Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion. So I'm going to briefly review the topic. Consider that we have a particle that's undergoing circular motion, as shown in the picture. We can decompose the acceleration of this particle into two components. One of them is the centripetal acceleration, pointing towards the center of the trajectory, and the other one is the tangential acceleration, that is tangential to the trajectory. The centripetal acceleration accounts for the change in direction of the velocity and is equal in magnitude to v squared divided by r, where r is the radius of the trajectory. And the tangential acceleration is equal to dv dt, and it accounts for the change in speed of the particle. So what we have in the exercise is a pendulum bob that has a mass of 2 kilograms and is attached to this to the pendulum itself, that is to a string that has, and the bob has an initial velocity of 8 meters per second when theta is equal to 0. Okay, and our goal is to find what is the tension in the string when theta is equal to 0, and also when theta is equal to 30 degrees. So what I'm going to do is to choose a random value of theta, and I'm going to draw the free body diagram on the pendulum bob. Okay, so notice that the forces that act on the pendulum bob in this case are the gravitational force that acts downwards, and also the tension force that acts pointing to the center of the trajectory, that is in the direction of the string. Okay, now notice that we can decompose this into two components. One that is centripetal, so one that points towards the center of the trajectory, and another one that is tangential. And actually I'm going to choose the tangential to be pointing upwards. Okay, to the centripetal direction I'm going to give the name r, and to the tangential direction I'm going to give the name theta. Okay, then we can decompose the forces into these two components. Now notice that this here is theta, so this here must be theta as well. So we have, in the r direction, we have the forces T plus mg times the sine of theta, and this is equal to m times the centripetal acceleration, which, as I said before, is v squared divided by 2. Also, in the theta direction, we only have mg times the cosine of theta, but notice that it's pointing downwards. Okay, so it's minus mg times sine of theta is equal to m times the centripetal acceleration at. Okay, so I'm going to use the first equation in order to calculate what is the tension when theta is equal to 0. So when theta is equal to 0, the sine of theta is 0, and t is equal to mv squared over 2. The mass is 2 kilograms. V is 8 meters per second. And then the tension must be equal to 64 newtons. This is the tension when theta is equal to 0. Now, when theta is equal to 30, things get a little bit more complicated, and the process is a little lengthier, so let's start. I'm going to start with the equation for the theta coordinate. where we have that AT, the tangential acceleration, is equal to G times the minus G times the cosine of theta. Notice that AT is dv dt, and I'm going to multiply it by V. So we have minus Vg cosine of theta. So we have V times dv dt is equal to minus V V is equal to dl dt G cosine theta, and I'm going to say what dl is. So notice that the trajectory is something like this. It's a circular trajectory. And dl is the element, of length, the element of the arc length, and we have that dl is equal to the radius of the trajectory, r, times d theta. So we have v times dv, I'm canceling out the dt's here, is equal to minus g cosine of theta r d theta. Okay, and we can integrate this from theta equals 0 when the velocity is the speed is 8 meters per second to theta equals 30 when the velocity is what we want to find. Notice that r is equal to 2 meters, so we can just substitute everything in the equation. So we have v squared over 2 minus 8 squared over 2 is equal to minus g r. Okay, and I'm gonna substitute the numbers. So we have g is 9.8 meters per second squared times r, which is 2 meters. And then we have to integrate. So we have sine of theta. We integrate cosine of theta. So we have sine of theta from 0 to 30. So we have that v squared is equal to 2 times 8 squared, that's 64 divided by 2, minus 9.8 times 2 meters, divided by 2, because the sine of 30 is 1/2. And actually, just to be consistent, I'm not going to use any unit here. Okay, I want to leave it implicit that I'm using the International System of Units. And v is equal to, actually v squared is equal to 44.4 meters squared per second squared. So this is the value of v squared when theta is equal to 30. And I'm now going to just go back to the equation for the r coordinate, substitute it there in order to find t. Now notice that t is equal to m times v squared over r minus g times sine of theta. So m is 2 kilograms. V squared is 44.4 meters squared, second squared, divided by 2 meters, minus 9.8 meters per second squared times sine of theta. So T is equal to 34.6 newtons. Okay, and this concludes our exercise.